Welcome to the deep dive. We're going deep on singularities today. We've got excerpts from all kinds of academic papers, physics, cosmology, even some applied mathematics in
A
there.
real mix.
Yeah.
It's going to be a wild ride.
It is. Get ready. We're going to try to figure out, well, first of all, what even are singularities,
Right.
the different forms they take, and how scientists are really trying to grapple with these points where, our normal everyday understanding of the universe just kind of breaks down.
Yeah, it's fascinating because this idea of a singularity, it pops up in so many different areas. It's this recurring theme where things just get a little bit crazy. Whether we're talking about black holes or even something as simple as a water droplet breaking apart.
Okay, well, before we go too far, let's back up a little bit. Define our terms here. What is a singularity? Because I feel like that's one of those terms that's thrown around a lot in science, but I'm not sure I can really explain it to somebody.
Yeah, and you're not alone, right? It's a tricky concept. Think about trying to divide by 0 in your calculator.
Yeah.
You get an error message.
Right.
That's kind of a simple example of a singularity. It's a point where a mathematical function just becomes undefined.
Okay.
And so now imagine that happening not in your calculator, but in the equations that describe the physical world.
Mm-hmm.
Things get really weird, to say the least.
So it's like the universe is hitting a divide by 0 error. That's a pretty wild way to think about it. And I know that some of our sources today dive deep into singularities and general relativity and cosmology. That's when it starts to feel really science fiction-y.
Right, exactly. In general relativity, the most common example of a singularity is at the center of a black hole.
Okay.
And you can picture it like this. It's a region in spacetime where gravity becomes so intense that not even light can escape.
Right.
We've all seen those popular images of black holes, those swirling masses with a dark center. Well, that center point, that's the singularity.
So the singularity is like the point of no return inside a black hole. Because I remember, learning about the event horizon.
Yeah.
That boundary beyond which nothing can come back.
Yeah, you're exactly right. And the Schwarzschild solution, which is kind of a mathematical description of a non-rotating black hole,
Okay.
actually describes this thing called a trapped surface.
Okay.
So think of it as a sphere around the singularity where gravity is so strong that even light gets trapped.
Yeah.
And this sphere, it's what we call the event horizon.
Got it. Okay. And the singularity itself is at the very center of that sphere.
Exactly. And that's where our current theories suggest that, well, density becomes infinite. And the laws of physics as we know them just cease to apply. It's almost like the universe is hitting a reset button.
Wow.
And it gets even more mind-boggling when we consider the Big Bang. The event that supposedly kicked off the entire universe.
Oh, yeah. Bring on the mind-boggling. So you're telling me the entire universe started from a singularity? That's even harder to wrap my head around than the black hole singularity.
Yeah, it's definitely one of the biggest puzzles in cosmology.
All right.
At that very first moment, the Big Bang theory suggests that the universe was compressed into this infinitely dense and hot singularity. And from that point, it began to expand, giving rise to everything we see today.
Okay, I need like a minute to process that. That's incredible. But also a little bit unsettling to think that everything, literally everything, might have come from a point where everything breaks down.
It is.
Our sources also mention that this idea of a singularity, particularly at the beginning of the universe, it's not universally accepted.
You're right. Some physicists are exploring these alternative theories that actually challenge the very existence of singularities.
Right.
And one of these alternatives is something called quantum hyperbolicity.
Okay.
And this emerges from loop quantum gravity, which is a theory that suggests that space itself is actually quantized.
Quantized,
Yeah.
Meaning what? Like it can only exist in specific chunks.
In a way, yes. It means that space comes in these tiny, indivisible chunks, kind of like pixels on a screen.
Oh, okay. So instead of the universe being smooth, like a sheet of paper, it's more like a digital image with limited resolution.
Exactly. That's a great analogy.
Mm-hmm.
And so this means that space might not be able to be infinitely squeezed.
Oh, okay. So quantum hyperbolicity is saying that because of this kind of digital nature of space, that might actually prevent singularities from even forming in the first place.
Right. So imagine instead of space collapsing into a single point, it kind of turns inside out at these incredibly high densities.
It turns inside out.
It's like reaching this limit where you just can't zoom in any further. Not because you've hit a point, but because the structure of space itself has changed.
That's wild. So it's a completely different way of thinking about what happens, at the Big Bang or inside a black hole.
Right.
But I'm guessing, as with any scientific theory, there's still debate about whether this is actually how things work.
Oh, absolutely. I mean, there's no definitive answer yet. Quantum hyperbolicity has its own complexities. And there are other theoretical frameworks out there that try to address the singularity problem in different ways.
Right.
It's still an area of very active research.
Yeah.
And there's a lot we don't know about what happens at these points where our current understanding breaks down.
So while these singularities might be these points of breakdown, they're also pushing scientists to come up with these new and more complete theories. It's like these points of crisis are actually driving scientific progress, which is pretty cool.
Yeah.
But it's not just in these vast reaches of space where we encounter singularities, right? Our sources also talk about them appearing in places that feel a bit more, well, ordinary.
You're absolutely right. I mean, singularities aren't just confined to black holes and the Big Bang. We actually see them in everyday phenomena, too, like the way fluids behave.
Wait, are we talking about something as simple as water, flowing from a faucet? How do singularities come into play there?
Yeah, exactly. Think about a single drop of water breaking off from a faucet. That moment of separation where that thin neck of water snaps, that's a singularity.
Ah.
To a point where that, smooth, continuous description of the water's shape just breaks down.
I never would have thought about it that way. But, I mean, it makes sense when you put it like that. We've all seen a drop of water break off. And it definitely doesn't happen in, a perfectly smooth and predictable way. There's that little wobble, that final snap. It's almost chaotic.
It is, and that's what makes it so interesting. And it's not just limited to water droplets either.
Okay.
The same principle applies to other fluids in all sorts of situations. The formation of shock waves, the way cracks propagate in materials, even the way a liquid jet breaks up into smaller droplets. These are all examples of singularities in fluid mechanics.
Okay, so we've got these singularities happening all over the place, from the heart of black holes to, our kitchen sinks. That's kind of amazing, this underlying connection. But how do scientists actually study these things, especially when, it involves those points of breakdown where our usual equations just don't work?
Right, yeah, that's where things get really clever.
Yeah.
So scientists use a combination of, mathematical tools and experimental observations to try to understand these singularities.
Okay.
And one important tool is something called asymptotic analysis.
Okay, yeah. I think we touched on that briefly earlier. Could you remind me what that is again?
Sure. Imagine you're looking at a map and you want to zoom in on a particular area to see more detail. Asymptotic analysis is kind of like that, but instead of a map, we're looking at mathematical equations.
Okay.
It allows us to zoom in, on the region near a singularity and see how those equations behave as they get closer and closer to that point of breakdown.
Got it.
It's like a way of understanding the essential behavior without getting bogged down by those infinities.
So it's like a mathematical magnifying glass for those tricky spots where things go to infinity.
That's a great way to put it.
Yeah.
And another key technique is stability analysis.
Okay.
And this helps us figure out which solutions to those equations are actually physically meaningful.
Right. So you mentioned this before, but it's basically like whether those mathematical solutions actually hold up in the real world, right?
Exactly. You see, a mathematical equation can often have multiple solutions,
Right.
but not all of them are going to be stable.
Mm-hmm.
A stable solution is one that persists even when you introduce small disturbances. So think about a ball at the bottom of a valley. If you nudge it slightly, it'll roll back to its original position. That's a stable system.
Right. But if that ball was perched precariously on top of a hill, even a tiny nudge would send it tumbling down. That would be an unstable system.
Exactly. And in the context of singularities, stability analysis helps us identify those solutions that are more likely to actually occur in nature. It's about separating the mathematically possible from the physically real.
So it's like weeding out the mathematical solutions that are just hypothetical and focusing on the ones that describe what we actually observe in the real world.
Exactly. And once we've identified those stable solutions, we can use things like numerical simulations to get an even deeper understanding.
Okay.
Simulations allow us to create these virtual models of these systems and see how they evolve over time. It's like running a virtual experiment on a computer.
So we're talking about creating a computer simulation of a black hole or a breaking water droplet. I can only imagine how complex those simulations must be.
They are incredibly complex, but with the power of modern computers, we can actually simulate these phenomena with remarkable detail.
Wow.
And gain insights that would be, impossible to obtain through those analytical methods alone.
It's pretty amazing how technology is allowing us to probe these mysteries of the universe that were just completely out of reach not that long ago. And it seems like there's a real back and forth between these different approaches, the mathematical analysis, the experimental observations, and the computer simulations. They all work together to give us a more complete picture.
Absolutely. It's
Yeah.
a very multifaceted approach.
Yeah.
And one area where this interplay has been particularly fruitful is in understanding the process of drop pinch-off.
Okay, so back to the dripping faucets. Earlier you mentioned how that final moment of separation is a singularity. Is there anything more to that story?
Yeah, there's a lot more to it than meets the eye.
Mm.
So scientists have discovered some really intriguing things about how those droplets actually break apart.
Okay.
It turns out that that final shape of that breaking thread of water, it's not random.
Okay.
It's actually governed by this universal scaling law.
A universal scaling law. So does that mean, like, there's some kind of underlying mathematical pattern to how those droplets break? Because I always thought it was more of just a chaotic, unpredictable process.
It seems that way, doesn't it?
Yeah.
But underneath that apparent randomness, there's this beautiful mathematical order. So the scaling law relates the minimum radius of that liquid thread to the time remaining before it breaks.
Okay.
And the incredible thing is that this relationship, it holds true regardless of the specific fluid properties or even the initial conditions.
So whether it's a drop of water, honey, or even something like molten metal, they all follow the same mathematical rule as they break apart.
That's right.
That's pretty mind-blowing. What's driving this hidden order?
It all comes down to the interplay between inertia and surface tension.
Okay.
Inertia wants to keep the fluid moving in a straight line, while surface tension acts to, minimize that surface area, pulling the liquid inwards. It's like this delicate tug of war between these two fundamental forces.
So it's a battle between the fluid wanting to keep moving and wanting to minimize its surface area. That's kind of an interesting way to think about it. But I'm guessing it's not always that simple, right?
You're right. It can get more complex. For example, when you introduce viscosity, that's the stickiness of a fluid.
Right.
The whole dynamic changes.
So something like honey, which is very viscous, would break apart differently than water, which has a lower viscosity.
Exactly. So highly viscous fluids, they tend to break apart much more slowly. And the shape of that breaking thread is different. Instead of that rapid, clean break, it's more of a gradual stretching and thinning process.
So the viscosity of the fluid actually changes the whole singularity picture. Does that mean, like, there are different types of singularities even within this seemingly simple process of a droplet breaking off?
That's a great observation.
Yeah.
And it highlights another fascinating aspect of singularities, their universality.
Universality, what does that mean in this context?
So it means that the fundamental structure of a singularity, the way it behaves near that point of breakdown, is often independent of the specific details of the system.
Okay.
It's like there's a common mathematical blueprint underlying all these seemingly diverse phenomena.
So whether we're talking about black holes, breaking water droplets, or shock waves, there are similar mathematical principles at play?
Yeah, that's right.
It's like there's a hidden unity to all these different types of singularities.
That's the beauty of it.
Yeah.
And it suggests that there's a deeper level of understanding to be gained by studying these points of breakdown. They might be where our current theories fail, but they're also where we might find clues to, new and more fundamental theories.
Okay, so we've explored these singularities in cosmology and fluid mechanics, even touched on pure math. Is there any other area we should look at before we wrap things up?
Well, there's one more area where singularities pop up that we haven't talked about yet, and it might surprise you.
Okay.
Shock waves.
Shock waves, like you mean those sonic booms from like supersonic jets, or those dramatic ripples you see in images of explosions? What do those have to do with singularities? I mean, they seem more like, a sudden burst of energy than a point where everything breaks down.
Right, and that's a great question. And it highlights how diverse this concept of a singularity can actually be. In the case of shock waves, the singularity lies in the fact that certain physical quantities like pressure, temperature, density, they experience this sudden discontinuous jump across the wavefront.
Okay.
It's like hitting a wall. But instead of a physical barrier, it's a sudden shift in the very fabric of, the physical world.
So even though we can see these, dramatic images of shock waves, the singularity itself is more about what's happening at that, like, incredibly thin boundary between the undisturbed air and the shock front, right?
Yeah, exactly.
It's like a discontinuity in the smooth flow of things.
That's a great way to put it. Yeah, the equations that describe that, smooth, continuous fluid flow, they actually break down at that shock front. just like they do at the center of a black hole. It's another example of those mathematical descriptions kind of hitting a wall.
Huh. It's amazing to think that there are these parallels between something as massive as a black hole and something like a sonic boom, right? I mean, they seem like completely different scales, but they both involve this idea of a sudden breakdown in our usual way of describing things.
Exactly.
Yep.
And what makes shock waves even more intriguing is that they involve this fascinating interplay between different areas of physics.
Oh.
You've got fluid dynamics, thermodynamics, even acoustics, all coming together in this really dramatic event.
It's like a symphony of physical forces.
It really is.
It sounds like there's a lot going on in a shockwave. Our sources mention some specific examples of how shockwaves are being studied and even used in technology, which is kind of cool. One that really caught my eye was the idea of imploding shockwaves.
Ah, yes.
Yeah.
That's an incredibly exciting area of research.
Yeah.
So imploding shock waves are being used in something called inertial confinement fusion, which is this potential pathway to clean energy.
Okay, so we're talking about like harnessing the power of these incredibly intense events to create energy. That sounds almost like science fiction.
It does have that futuristic feel, doesn't it? So
Yeah.
the idea is to focus a powerful shock wave onto this tiny target containing hydrogen isotopes.
Okay.
And as that shock wave implodes, it creates these incredibly high pressures and temperatures, which can actually trigger nuclear fusion reactions.
Oh, wow. So it's like creating a miniature star in the lab and then harnessing the energy released from those fusion reactions.
That's the goal. It's a challenging process. There are a lot of technical hurdles to overcome,
Right.
but the potential payoff is huge. I mean, clean, abundant energy from a process that powers the stars themselves.
That's pretty incredible. But it's not just about futuristic energy sources, right?
Yeah.
Our sources also mention some more down-to-earth applications of shock waves, like in medicine.
You're right. So lithotripsy, which is this non-invasive medical procedure, uses focused shock waves to break up kidney stones
Oh, okay.
into smaller pieces that can then be passed naturally. It's a remarkable example of how a deep understanding of this seemingly exotic phenomenon can have these direct benefits for human health.
It's like we've gone from this grand scale of the cosmos down to this very personal level of treating a medical condition. And singularities have played a role in all of it. It's a reminder that these points of breakdown, these places where our understanding falters, they aren't just abstract concepts, right?
Right.
They have this potential to impact our lives in very real ways.
I think that's a really important point to emphasize. Singularities, they might represent a failure of our current theories, but they also offer this glimpse into something deeper, something more fundamental about the universe. They challenge us to think beyond our current understanding and to develop new tools and frameworks, to really explore the unknown.
Yeah, I'm leaving this deep dive with a sense of awe and also a healthy dose of intellectual humility.
Right.
We've explored these singularities in cosmology, in fluid mechanics. We even touched on the world of pure math.
Yes.
And in each case, they've pushed the boundaries of our knowledge and sparked all these new questions. And who knows what other types of singularities might be lurking out there, just waiting to be discovered, or how our understanding of these points of breakdown might shape the future of science and technology.
Well said.
That's a great note to end on, I think. A sense of wonder and a call to keep exploring. Thanks for joining us on this incredible journey into the world of singularities. And, remember, sometimes it's in those moments of breakdown, those moments where things fall apart, that we actually find the most profound insights.
Until next time, keep diving deep.